Okay. Just another problem we solved. X squared plus 7x plus 6 equals 0. Very easily done. B is 7, so we put 7 in for B here, and here we get -7, we get 7. We put 1 in for A, and that goes here. We put the 6 in for C, that goes here, and of course the 4 is part of the formula of the 4AC. So there's our 4AC, and here's our 2 times A, 2 times 1. Simplify what's inside of the parentheses. 49 minus 24 is 25. You get -7 plus or minus the square root of 25 over 2. -7 plus or minus 5 over 2, which is -7 plus 5 over 2, or -7 minus 5 over 2. And -7 plus 5 is -1, so we get, -2, so we get -2 over 2, which is -1. -7 minus 5 over 2 is -12 over 2, which gives us -6. So that should be fairly straightforward. Now we'll illustrate a couple of other things here. Okay, I'm going to solve x squared plus 5x plus 7 equals 0. Okay, B is 5, so B goes here and here. A is 1, C is 7, so there's our 4AC with a minus. And 2 times A is 2 times 1, so that's all straightforward. Turns out, though, when we do this, we get -3, and -3 is not the square of any real number. Because when you square any real number, whether it's positive or negative, you're going to get a positive, and hopefully you're very familiar with that. So you can't square any real number and get -3. So you could say, well, the solution, there's no real number solution. And that's important if you're going to graph the parabola that's given by this expression. You're not going to have an x-intercept, but that comes later. If, though, you want a complete solution to this, and the complete solution to this thing is very important, even though it seems weird, you say, okay, well, can't do the square root of -3, but I'm going to write this as -3 is 3 times -1, so that I can write the square root of this as square root of 3 times square root of -1. Okay, well, what good does that do? Well, square root of 3 I can do. I mean, I can't do it exactly, but I can approximate it with a calculator. It is a real number. It's irrational, so you can never write it completely as a decimal number, but you can approximate it as closely as you wish. Okay, so that's a perfectly good number. Now what about this square root of -1? I'm going to say, okay, not a real number, let's call it imaginary. It's an imaginary number. And the square root of -1 is the basic imaginary number, I. I for imaginary. Okay, so now we have the number square root of 3 times I, which is an imaginary number. Square root of 3 times your basic imaginary number, square root of -1, or I. As I mentioned in class, this is incredibly important. Without this convention, without these imaginary numbers, most of the advanced engineering that we rely on today would have been impossible to develop. Theoretically, it could have been developed without it, but people's minds just would not have been able to develop it at the pace they have. We'd be back in the early 20th century, 100 years ago, right now, had it not been for this convention. So it's really important. Many of you won't ever encounter it, but if you're going to go into engineering or many of the sciences, you will, and you're going to understand later how important it is. So anyhow, we have this, and this then is -5/2, distributing the division by 2, -5/2, plus or minus the square root of 3i divided by 2, which we write as square root of 3 over 2 times I. A question came up. You put the I after the number or before the number? Answer is, doesn't matter, because multiplication is commutative, even with imaginary numbers. Doesn't matter which order those are in. As long as the I is attached to the square root of 3 over 2, you're okay. All right, well, that's a solution. And then I had everybody work another problem. Here it is, and here's the quadratic form. And I wrote it again because when I looked at it on my screen, it was a little hard to read up there for some reason. So I wrote it bigger, make sure everybody could read it. So just superfluous up here. Okay, so we just plug in the numbers into the quadratic formula. That's all very straightforward. All you got to do is practice it, be able to identify what's in front of x squared, what's in front of x, and what else you've got. And then we simplify, and we end up with 3 plus or minus the square root of negative 11 over 2. Well, we do just what we did over here. We do the square root of 11 times negative 1 to replace the square root of negative 11. And then we do square root of 11 times square root of negative 1, which gives us square root of 11 times I. So here's our final solution. One thing we didn't do before, we didn't have a negative here, but a negative of a negative gives us a positive. Make sure we understand that. So anyhow, here's our solution set. 3 plus or minus the square root of 11 over 2, 11 I all over 2. We distribute the division by 2, and we get 3 halves plus the square root of 11 over 2I for the plus, 3 halves minus the square root of 11 over 2I for the minus. Now, these numbers here are called complex conjugates. Okay, because you probably see that notation, or that terminology. Let me just deconstruct that for you. These are complex numbers being real number plus imaginary number. Real plus imaginary. Now there's a minus there, but it's plus a negative imaginary if you wish. Okay. They're complex, and they're conjugates because it's the same number plus the imaginary number and the same number minus that imaginary number. Okay, those are complex conjugates, and anytime you have a complex solution to a quadratic, you're going to have the same number over here with a plus, and then with a minus, you're going to have complex conjugates. Okay, important notation. One little blurb about graphing of quadratic functions. If you have f of x equals our x squared plus 5x plus 6 function, for example, you know that x is then going to give you be equal to negative 5 plus or minus the square root of 1 over 2. And you know where the zeros are going to be at negative 2 and negative 3. That's kind of the way I drew it, but not really. But an important aspect of the graph of a quadratic function, okay, a quadratic function always gives you a parabolic graph. So you can think of this as taking your extended basic function graph and moving it somewhere and maybe stretching it. Or even your complete basic function graph. Okay, the vertex is the low point or the high point of the parabola. Okay, it's the point on the axis of symmetry. You've got symmetry about the y-axis here, and this is the point on the axis of symmetry. It'll always be either the low point or the high point of your parabola. The axis of symmetry comes right out of the expression of the quadratic formula. It's right here, negative 5 halves. Okay, there are reasons for this, but I'm just alerting you to the fact that the negative b divided by the 2a is where your axis of symmetry is going to be. In this case, it's negative 5 halves, so here's the line, x equals negative 5 halves, so this parabola is going to move over to where its vertex is on this line. That might be above the x-axis, it might be below the x-axis. In this case, it's a little below the x-axis. Now, and you can figure out where that is just by plugging in negative 5 halves up here and figure out what the y-coordinate would be. So that's worth knowing because that's kind of central to some things you want to know about graphs of quadratic functions.